So we have seen in the synchronous machine that you have a stator winding, which is supplied with AC, and then you have a field winding which is given DC. And since the field structure is going to be rotated and you want to supply DC to it, you need to supply it through slip rings, as we had seen earlier. We went to synchronous machine because the DC machine had to be supplied with the DC given to the armature, which is going to be rotating, and the armature is the main seat of electromechanical energy conversion. Therefore, the full output power that needs to be sent into the mechanical side has to go into the armature, which means it has to go through the brushes and commutator. This, we said, can give rise to difficulties due to sparking and brush wear and all that, and instead we flip the machine around and put the armature on the stator and the field winding on the rotor. But nevertheless, we'll have to supply the field with slip rings. This is not so bad as that of a DC machine because the field winding is continuously supplied with constant DC. There are no interruptions to the field excitation. But nevertheless, now that we have seen that if you excite the stator winding with AC, you are producing a rotating magnetic field, which is therefore varying with respect to time, as seen by the rotor. You have the rotor, and the field would be rotating, and therefore the rotor would see a field variation with respect to time. One might ask the question, why not generate a field excitation or some current in the rotor to generate a magnetic field through induction itself? Right? Why is it necessary to supply the field through a separate DC excitation outside? We can avoid the slip rings completely if we are able to produce this field by induction. The answer to that therefore gives rise to a very different variety of a machine. So let's see what happens when you are having a field that is rotating and you have some conductors on the rotor which will then see an induced EMF. So we have seen that the field that is going to be generated is predominantly a sinusoidal magnetic field. So let's consider that you have on the machine, so this is the geometry of the machine, and you have the rotor inside, right? And let us say that you then have a rotating magnetic field inside the air gap. So the air gap inside has a rotating magnetic field. Okay, let's mark the direction of rotation as anti-clockwise. And then let us consider further that you have a conductor here and here. So let's say that the magnetic field is a two-pole field, and you have two conductors being coil sides of one coil placed 180 degrees apart as is shown here. So we can now draw a developed view for this, which would be so let us say that this is the midpoint, which we consider phi equal to 0. So let us call this axis as phi equal to 0, and phi increases this way. So we have one conductor that is placed 90 degrees away, which let us say is here, and then another conductor placed at minus 90 degrees, that is here, and then you have the magnetic field which is going to exhibit a sinusoidal variation, and therefore the maximum value of the magnetic field, let us say at the instant that we are considering, occurs at phi equal to 0, and therefore you have a magnetic field which goes down like that. This is the magnetic field. Let us say that what we have drawn is the flux density waveform. Remember that the MMF waveform and the flux density waveform are the same, and therefore this is how it looks. Now therefore, since this let's call this as coil side C11, and then this is C1, coil side C1, C1 dash. So coil C1, C1 dash is therefore having a flux linkage, because there is a magnetic field that is now being felt by this. How do we determine what is the flux linkage? So in order to determine the flux linkage, what one can do is consider the cylinder of the machine. This is the machine cylinder, and in order to consider the flux linkage, what we need to see is find out how much flux is going to enter the rotor through this region, and all the flux that enters the rotor through this region will then go into the rotor and come out on the other side. And therefore, if we find the flux that is entering the rotor there, that multiplied by the number of turns would then give us the flux linkage. And in order to find out the flux that is entering, since this is not a uniform flux density, if it was a uniform flux density, we could simply multiply that flux density by the circumferential area that is seen there, and that would be the total flux. But now it is not a uniform flux density, and therefore we'll have to resort to integration. And let us consider a small elemental area. The elemental area therefore looks like this, that at a length at an angle phi, at an angle some phi, let's consider a small d phi around it, and there is this length that then goes across the machine. So whatever flux is entering into that area due to the flux density distribution, remember that this flux density distribution exists all along the length of the machine, and if you are going to have flux that is entering the rotor, it will enter the rotor all along this length. So the area that we are therefore looking at for the flux entering the rotor can be defined as R multiplied by L, or R into d phi is the length of the arc that you have here. It is the length of the arc that you have here, and that multiplied by the length along the axis of the machine is the area through which field is entering into the rotor, and therefore this multiplied by the length is the, so this is the area multiplied by flux at the point phi is the total flux that is entering. That multiplied by the number of turns is then the flux that is this multiplied by n is the elemental flux linkage caused due to the flux flowing through the elemental area. And if we now want to find out, so B of phi, as we can see from the distribution that is that we have drawn, is simply Bm into cos phi. So we can therefore write d psi as n into r into L into Bm cos phi d phi. And therefore the overall flux linkage psi is then given by d psi into integrate from, we need to integrate from this point, that is we need to integrate from this point to this point anti-clockwise direction, from here to here, and therefore we need the limits as minus pi by 2 to pi by 2 of d psi, which is therefore equal to n into r into L into Bm into integral minus pi by 2 to pi by 2 cos phi d phi. We need to include the functionality with respect to time as well. Actually, this is then at omega st equal to 0. If we are going to have B as a function of time and phi, this would be Bm cos phi minus omega st, and therefore we write this functionality as cos of phi minus omega st dt, and we are doing this integration at a given instant of time. At this particular instant, the way we have drawn it, this instant represents omega t equal to 0. So let us just retain this functionality omega s into time. It is invariant as far as the integration is concerned. The integration is with respect to phi to find out the flux linkage, and therefore we can write this as n into r into L into Bm sine of phi minus omega st going from minus pi by 2 to pi by 2, which is nRL into Bm into sine of pi by 2 minus omega st minus sine minus pi by 2 minus omega st, which is n into r into L into Bm cos omega st plus cos omega st, which is 2 times Bm n r L into cos of omega st. So this is then the flux linkage that is going to be there. As time varies, definitely the flux linkage is going to change because you have Bm being dependent on variation of time as well. So now, if this is the flux linkage, one can now look at the induced EMF. Induced EMF is given as minus d psi by dt, which is then 2 times Bm n r into L into omega s into sine omega st. So we find that the induced EMF is a function of speed and a function of flux density as well, and other things that are dependent on the geometry of the machine, L and R, and N is the number of turns as well. Now let us say that this waveform is going to be moving. Let me just copy this waveform. Now this is induced EMF, and because of this induced EMF there is now going to be a flow of current, and this flow of current will be in such a direction. Now if Bm is going to decrease, then you will find that the direction of current, or if the flux linkage is going to decrease, the flow of current due to this induced EMF has to be in a sense so as to increase the flux density. Now we know that this Bm, that is the waveform of flux density, is a moving flux density, and therefore after some time you would have the flux density having moved, let us say, to this position. Now this induced EMF will then cause a flow of I in this loop such that that flow of current generates a flux in this direction so as to increase the flux levels that is now being reduced because of the flux density moving away. And therefore, in order to cause a current flowing in this, in order to cause a flux in that direction, there will be an induced current, and that will have to flow in this direction, that is a dot here and a cross here, right? So you would have a dot here and a cross here, and now therefore, because there is a flow of current in C1 and C1 dash, and there is some flux density in the region of C1 and C1 dash, here flux density is negative and here flux density is greater than 0, and therefore each of these will experience then a force. What would be the direction of the force? You apply this rule IdL into B. So the direction of force will be I into dl cross B, will then this will C1 dash will experience a force to the right hand side, and let's look at C1. C1 has a current flowing into the board, and you have flux density that is more than 0, and therefore C1 will also experience a force in this direction, right? So due to the movement of the magnetic field in this direction to the right, going from 0 towards positive phi, then you have, if the field is moving like that, then you have a force that is experienced by C1 and C1 dash that is also attempting to move it along with the direction, along the same direction as the movement of the flux itself. Now let us say that maybe the flux density, if it moves in the opposite direction, then what will happen? Now let's say that the flux density is moving, has moved such that it is now here. If the flux density has moved here, that means flux is moving to the left. If flux density is moving to the left, then also E induced EMF is still given by minus d psi by dt, which is a mathematical expression, and flow of current will also again have to be such that it boosts the flux, that is a flux linkage in C1 C1 dash. Movement to the left of the air gap flux density also brings down the flux linkage, and therefore the flow of current has to be so as to increase the level of flux linkage, and it's in the same direction therefore. But nevertheless, now what is happening is the flux density in the region of C1 dash is now greater than 0, whereas flux density in the region of C1 is now less than 0. If this is the case, the direction of the force on C1 is now reversed, and C1 will face a force that is tending to move it in the left direction. C1 dash also has a force that tends to move it towards the left. Therefore, what we can see is that if you have C1 dash and you have a flux density waveform that is moving along either direction, you see that there is a force felt by both coil sides C1 and C1 dash, which tend to move it in the same direction as the magnetic field. Movement. So to say that the movement of the field attempts to drag the coils C1 and C1 dash in the same direction. Now, looking at it from the viewpoint of the rotational system, of which we have drawn a developed view, in the case of a rotational system, what it would mean is that if the flux density is moving in the anti-clockwise direction, then the C1 and C1 dash, so this is C1 and C1 dash, C1 will face a force this way, C1 dash is going to face a force this way, and therefore there will be a electromagnetic torque that is felt, which will attempt to rotate the rotor to which C1 and C1 dash are attached. This is C1 dash. So we find that if the flux density is going to move and you have conductors C1 and C1 dash that are placed, then there is a force tending to move the conductors along in the same direction. Now, if there is a torque that is felt by the conductors and the conductor is going to move, then it means that these expressions are no longer applicable, because when this conductor is also beginning to move, that will affect the flux linkage in the conductor. Therefore, we now have to revise the estimate of the flux linkage in the conductor. That we will see in the next module.